Hello, my name is Sebastian Raveau from Pontificia Universidad Católica de Chile, and today I'm going to talk to you about modeling route and mode choices in a public transportation system. This is a joint work with my advisor, Juan Carlos Muñoz, Juan de Sotuza, also from Pontificia Universidad Católica de Chile, and with the collaboration of Nadia Wilson from MIT. And this project comes from the LT5 project of the BRT Center of Excellence regarding modeling reliability, cost, travel times, safety, comfort, and other relevant variables on modal and route choices. So, first of all, what I mean with modeling mode and route choice. Let's take, for example, the Tokyo subway system, and let's assume you have to travel from two given stations, any of them, and you don't know anything about the network. The first approach would be, okay, let's see the map and try to figure out a way to get from origin to destination. If you have more information, maybe you can take into account other attributes such as travel times, number of transfers, comfort, crowding levels, etc. And we know that some people follow different criteria when choosing how to travel from a given point to a destination. For example, the fastest way, the cheapest way, if there's fare involved. In transit context, you can add some other factors such as avoiding walking, avoiding transferring, but most of the people consider these attributes and the others at the same time. And a given shortcoming of the current planning tools is, for example, the Santiago metro system. When you go to the website and you tell the system, okay, I want to travel from this station to that station, the system only gives you two alternatives for choosing a route: the fastest way and the one with the least transfers, and that's it. It doesn't take into account any other variables, which are important. So the objectives of this study are mainly to identify and quantify the factors that affect the transit user behavior, explore differences across modes, particularly those competing with BRT, and maybe compare the preferences of transit users in different systems and contexts. So this presentation, I will start with some route choice background that will present some important variables that we think should be taken into account when addressing these kind of questions. I'll present a study case. I'll show some results and perform some analysis of what we got, some extension applications, and finally, briefly, the future work that we have to do from now. So, what is usually done when modeling route choices? Traditional variables are taken into account. These are the key elements when modeling behavior, such as travel times, the fare, the number of transfers, and sometimes, if the modeler has the data, you can refine them with socioeconomic characteristics, such as income, gender, purpose of the trip. But we also know that there are other aspects that also influence the decisions, such as comfort and safety, maybe transfer accessibility, network topology, some things like aesthetics. But the problem with these variables is that they're subjective and really hard to quantify. For example, we don't have a scale for measuring comfort, even though we know it's important. So, what we do think people take into account, first of all, the in-vehicle time. People want to get to the destination as fast as possible. Also the waiting time, the specific stops along the way. Walking time, and we consider walking time especially when transferring. And these are all travel time components. Also the number of transfers. People want to avoid transferring as possible. But not only the amount of transfers, but the quality of the transfers. For example, the station layout. If you have to go up when transferring, maybe the transfer is at level, which is the easiest one, or maybe you have to go down when transferring. Also the infrastructure, such as when transferring, you can get an assisted help, such as an escalator or an elevator. Maybe the transfer is semi-assisted, which is partially done on an escalator or elevator and partially walking, or the worst case, in this sense, the non-assisted, in which you have to walk all the way. And these variables have to do with transfer experience. Also the mean occupancy as a proxy of the comfort. The possibility of not boarding, how we model this. For example, we took data from the Santiago metro system and we saw that when the occupancy in the train at the station is 85% or more, there's a chance that the traveler won't be able to board and maybe have to wait for the next train. And on the other hand, maybe there's a possibility of getting a seat. And also, using data from Santiago Metro system, we saw that when the train has occupancy of 15% or less, there's a chance that you might get a seat. And this all have to do with comfort and crowding. Also things like route distance. If you don't know much about the system, and your first approach to the travel you want to make is the map, maybe you go to the map and try to find the route that's the shortest one. Because a short distance may be a short travel time. So this is also important. The number of stations. Maybe you can count different stations along the way and choose the route that has the less stops. And angular cost. This is something that we defined as a measure of how direct a given route is. And this is defined as a product of distances and size of angles, which really don't mean anything to you. So let's see an example. Let's assume we want to travel from one origin to one destination. Unfortunately, there's not a straight line that connects both stations, so we have to go through 2 transfer stations on the way. The ideal would be travel directly. We can't, we have to transfer, and we have to travel to this station, so there's an angle. I want to go in that direction, instead I'm going in a different direction. An angle is formed. So we consider the angle and also the distance we're traveling along the way, and we have a first penalty for this given trip. Once we're in the first station, again, we would like to go straight to the destination. Once again, we can't. We have to go to the second station, so a second penalty appears related to the distance we're traveling in that direction and the angle that's formed between where I want to go and where I'm actually going. Finally, when we get to the second station, now we can finally travel to the destination, so there's no additional penalty terms. So for this example, this really simple case, that will be the expression for the angular cost. I'm not sure how direct this route is. And finally, we identify some routes that appear to be reasonable or not reasonable. And we define non-reasonable as a route that, for example, seems to take you away from the destination, or a route that along the way has the impression of going back to where it comes from. And all these last 4 variables are associated with the topology of the network. And the good thing is that all these variables that I showed, which are really not taken into account traditionally when modeling these kind of decisions, are really easy to obtain. For example, for the station layout, you just have to go to the station and see if it's an apple, an ascending transfer, a descending transfer. If you want to calculate, for example, the angular cost, all you need is the topology and distances and angles, which are really easy to calculate. So all this information is pretty much free. You don't need expensive service to get this information. So we took this model and we applied it to the Santiago Metro system based on a survey that Metro conducted in 2008. We focused only on peak hour trips, and we got pretty much about 93,000 respondents, but we are not interested in all of them. Only the people that transfer can make a decision, because if you're making a trip in which you don't have to transfer, you don't have any route to choose. You just travel along that line and that's it. So the people that actually can have to transfer, it's the people we are interested in. And we analyzed those travels, and we found that almost 40% of these people actually had to choose or chose 2 or more routes from the same origin to the same destination. Another thing we want to understand is the impact of the schematic map that appears in our station on the decisions. For example, this is the real topology of the network, and that's the map that's shown in every station. So people, this is what they see when they ride in the Santiago Metro system. And you can see that some distortion, especially in downtown area, which is the area shown in the circle, and this distortion may induce people to do things that are not good for them or not appropriate for the given trip. So we applied a simple multinomial logic model for the route choices. For every OD pair, we check the set of alternatives where the actual routes that the travelers chose, and we compare two models. A base model, which only has traditional variables, such as waiting time, travel time, number of transfers, and that's it. With our proposed model, has all the variables I showed before. Very briefly, the results, all the variables that we propose are significant, which means that all of these attributes help to explain, at some level, the decision of the people. All of them are important. Not only the travel times and the fares and the transfer are important, but there's a wide variety of things that people do take into account. Also, our model that has more variables is superior in terms of goodness of fit and forecasting capability. For example, the mean squared error when using both models to forecast is reduced to half when we use our model instead of the base model with only traditional variables. And finally, all the topological variables explain better the decisions when they're specified using the map instead of the real topology. So the map is important. People do have in their minds the map, not the real topology. So any distortion in the map do induce some decisions that may not be optimal for the system or for the given trouble. What else can we get? We can get marginal rest of substitution, for example, for analyzing how people perceive the different time components. In the base model, which doesn't include the walking time with transferring, we only have a waiting evaluation, which is pretty much 3.5 minutes of travel. When we use the fairly specified model, the complete model, we get that 1 minute of waiting is only 1.4, not 3.6 minutes of travel. So there's a bias, an important bias, when important information is not present in the model. And for the walking, we see that, okay, 1 minute walking for the people, it's pretty much 1.6 minutes of travel. Regarding the transfer, we have a wide variety of transfer depending on the characteristics, and we can take for each specific transfer evaluation in terms of, for example, travel time. How do we read this information? For example, let's take a transfer that's ascending, assisted, and on which you have the possibility of getting a seat. So to avoid this kind of transfer, the travelers are willing to travel 9 more minutes inside the trains, so they don't have to do this kind of transfer. And we have a wide variety of numbers that goes from 6.6 to almost 17 minutes. And in the base model, which only has the number of transfers and no more information about the transfers, we got only one valuation of 11.8 minutes of travel. So we presented the information to the Santiago Metro authorities, and we said, okay, there's a problem in the map, especially in the center of the city, and they do change the map. They listen to us and they change the map, and now this distortion is much smaller. What else can we do? We can apply this model to different cities and systems and compare the behavior on each city. For example, we're already working with some information with the San Francisco Bay Area, and we had some contacts with the Seoul metro system as well. We can apply this to a more dense network because the Santiago metro network is quite small. And we saw that as the number of alternatives grows, for example, for 2, which is the minimal number of alternatives, when you have a decision to up to 4, the proposed model is always better than the base model, but also the mean square error is much smaller relatively to the base model. So the bigger the network, the bigger the advantages of using the proposed model. We can also apply it to a more distorted network, because if you calculate the correlation between the distances, the real distances in Santiago and the map distances, it's quite high, it's 94%. But if, for example, you go to the London Underground system, it's only 22%. That's the real London Underground, and that's the map that's presented in every station, the famous London Underground map. And we got some data with the help from Nigel Wilson, so we were able to compare how people behave in both cities. What we found, for example, that in London, people value more waiting than in Santiago, but Santiago people care more about walking than in London. So there's some differences about how people perceive. One transfer, one basic transfer, is pretty much the same in both cities, 6.6, which is very interesting. in London, people do care much about occupancy. They don't like traveling in crowded trains. Santiago travelers are more willing to travel in crowded trains. They do care more about getting a seat, and they do care more about not boarding than in London. And regarding the topological variables, stations or this issue related to how reasonable the route is, all these are bigger in London than in Santiago, which is expectable because the London underground map is much more distorted than Santiago, as I showed before. Regarding transfers, in London we do have more types of transfers, but for each case the evaluations are lower than in Santiago. For the same kind of transfer, people value less the transfer in London than in Santiago. There's a difference in the behavior of the people. What else can we do? We can use this model for map design optimization, and this is something we're doing right now. For example, this was the network 2008 when the survey was taken, but currently Santiago Metro is building 2 new lines, the purple and the orange. So when these 2 new lines are built, a new map will have to be designed, and maybe we can use this kind of a tool to design the map so the travelers are induced to do certain decisions. For example, avoiding the most crowded line or other kind of decisions. We can also provide relevant information for the travelers. The most simplest one is provide information regarding the next the waiting times when the next bus is coming. This is something that's done all around the world, but not in Santiago. So this is the key element that should be given to the users. Maybe they can provide information about the stations and the environment, so they know if they're wheelchair accessible, how much they have to walk, and what they can find around the station. And for example, we can also provide information for certain disruptions. When a line has to be shut down, how do people that were going to use that line, how they can travel to different routes, so you have to provide information of, okay, which are the alternatives, how can I get to the destination avoiding this line, or other kind of information that's really important for this kind of disruptions. And finally, what's the next step on this research? We conducted a survey last year, 2 years ago, actually, 2011, in Santiago for the whole transit system. And we had a much bigger mode choice, first of all, when the users had to choose between feeder buses, trunk buses, limited stop buses, maybe the metro or a combination of the above, and also, of course, the route, the specific transit points from origin to destination. And the idea is to perform a similar analysis of the one we did in metro, but for the whole Transantiago system in the city. Okay, if you have any questions, this is our contact information, and we are eager to hear from you.